Thank you. Thanks for coming. Thanks, everybody, for being here. And of course, thanks to the organizers. This has been just such a fun conference, and so I really appreciate all the effort that everybody's put into it. So I'm going to tell you a story about multicrossing numbers of knots and turning knots into flowers. And this is just a story of me stumbling across some stuff about 8 years ago and sort of where it's led. And it's really been a lot of fun. And a lot of the work has been done with students, as I will explain as we go along. And when I say students, I actually mean undergraduates. But as you'll see, very, very talented undergraduates, as it turns out. So let me just start by talking a little bit about knots. I realize not everybody here, although there is a subset who know a lot about knots, not everybody thinks about knots every day. So typically when you draw pictures of knots, it looks like this, okay? And you have places where you leave a little break in the knot because you want to make it clear that this crosses over that under. And you always have these crossings where there are two strands crossing. So it looks something like that or something like that. Notice there's really only one type of crossing if I allow rotation. So my crossing either looks like that or it looks like that. So really, when I think about these crossings, these double crossings, what I'll call them, where two strands cross, there's really only one type of those things, okay? But this is the way people have been thinking about knots for 150 years. Kurt Reidemeister pointed out a very important fact, which is that if you have different projections of the same knot, you can actually get from one to the other by what are called Reidemeister moves. And I'm going to tell you about Reidemeister moves for those of you who are unfamiliar with them. You can do certain things to a diagram of a knot, and it doesn't change which knot it is. So for instance, you can do a type 1 move where I take a part of the strand of the knot and just put a little twist in it. That's not going to change the knot because I haven't passed the knot through itself. You can do a type 2 move where you take two strands of the knot and slide one over the other. And you can do a type 3 move where you take a strand, look at this back strand that you see right back here, and you push it down past the crossing. That's called a type 3 move, okay? And it's pretty clear when you look at these pictures that those moves are not going to change the knot. They change the picture of the knot, but they don't change the knot. So Reidemeister moves do not change the knot. Now, what Reidemeister proved was, in fact, it goes the other way as well. Namely, it's true that if you have two different pictures of the same knot, there has to be a sequence of Reidemeister moves from one to the other. I don't know what it is, so if this particular picture over here is a picture of knot K, this is a different picture of knot K, there has to be a sequence 1, 2, 1, 1, 3, 2, who knows what it is, to get from one to the other, okay? And this is really a powerful tool because it says if you're trying to understand a given knot, if you understand Reidemeister moves, that's going to tell you a lot. And we're going to use that to our advantage. Now, there's one other fact that I need before we get started, and that is I need to know that if you take a picture of a knot, we can take any projection of a picture of a knot, and if I'm allowed to change the crossings, I can turn it into the trivial knot. And so you see this particular knot right here. This is the 818 knot. And I claim that if I'm allowed to change the crossings on that thing, I can turn it into the trivial knot. And here's how I do it. What I do is I get on the knot at a particular point, like right here. I start traveling along the knot. And each time I get to a crossing, the first time, I change it into an overcrossing. So in this picture here, you'll see, first time I hit this crossing, I now change that into an overcrossing. That was already an overcrossing. I didn't change it. This one I have to change. It's an overcrossing, 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 overcrossing. This one I already changed. I'm not going to change it again, okay? So once I go through, and then I just keep going down. And if I do that, you'll notice I always think of this as like a roller coaster that runs by gravity as you sort of go down from the top point. Down, 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 until you get to the bottom. Take an elevator to the top. And if you think about what that would look like from the side, it is a trivial knot, okay? So every knot can be turned into a trivial knot just by changing crossings in any projection of the knot. And we'll use that in just a second. Okay, so the story begins, as I said, about 8 years ago. I was teaching a course on graph theory, and I was looking for papers that my students would be able to read. These are undergraduate students. And I stumbled across this paper on the archive called Triple Crossing Numbers of Graphs. Which, interestingly enough, is still on the archive. It's never actually appeared anywhere. I don't know why. But anyway, by Tanaka and Terragato. And one of the things graph theorists want to do is if they have a non-planar graph, they want to try to draw it in as simple a picture as possible. Okay? So in particular, this is a very famous graph called the Peterson graph. And this particular graph is a non-planar graph, but you can draw it such that it only has two crossings, two places where edges cross each other. Okay? So it's a relatively simple picture of that particular graph. But what these two mathematicians realized is you can do the following thing where you take this edge right here and pull it around the back, and you can create one triple crossing instead of two double crossings. And in some sense, that's a simpler picture if you allow triple crossings rather than just double crossings. And that's what this paper was about, this idea of, well, let's allow triple crossings and let's see if we can draw simpler pictures. Now, me as a knot theorist, I read this and I think, wait a minute. Can you do this with knots? do not have triple crossing pictures. And so it's sort of a really interesting thing, and it's very interesting how it grew out of graph theory to start. So in particular, we're going to have a triple crossing. A triple crossing from the top view looks like this. All of the strands have to go straight through. You can't go in and bounce off. You have to go straight through, bisect the crossing. T stands for top, M stands for middle, B stands for bottom. If you move things just a little bit, it's going to look like this, okay? So it resolves into 3 double crossings, okay? There are 2 different kinds of triple crossings. You can have a TMB triple crossing when you read it clockwise, or you can have a BMT triple crossing when you read it clockwise. So that's different than what happened with double crossings where there's only one of them. There's now 2 of these, although they're reflection equivalent. The way I remember them is TMB stands for Texas Medical Board, and BMT stands for basal metabolic temperature, okay? I ran into somebody actually last week who grew up in New York, and he said, no, that's not what BMT stands for. It stands for Brooklyn, Manhattan Transportation, I guess. So he was pretty sure about that. And so we'll say a projection with only triple crossings is called a triple crossing projection, okay? So here's some examples. Trefoil knot, figure 8 knot. Here are their triple crossing projections, okay? And you'll notice they look the same, which is kind of interesting. They both look exactly the same. The difference is on the bottom, it's hard to tell because the T goes right through. On the bottom, this one is a BMT. This one is also a BMT. But on the top, this one is a BMT, and this one is a TMB, okay? So they are actually different because of the way that the strands are labeled, okay? So these are triple crossing projections of those knots. So the obvious first question you're going to ask is, does every knot have a triple crossing projection, right? So here's some knot. Is it true that I can take that knot and turn it into a knot, into a projection that has just triple crossing? So that's the very first question you want to ask. And I'm going to use this idea of what is called a collection of crossing covering circles. There's a lot of C's in that, and I will mess it up eventually when I try to say it 3 times fast. But it's a collection of crossing covering circles. And what this is you take a projection of a knot, and you're looking for a set of circles that are disjoint, that bisect each of the crossings. So every crossing is covered by one of these circles, and that circle has to pass straight through the crossing. So this particular example here, I've hit these 3 crossings with this circle, these 2 with this circle, these 2 with this circle. So in all these examples, these are what I would call collections of crossing covering circles. Now, what's the advantage of having crossing covering circles? It turns out that I can take each circle and I can turn all of the double crossings that occur along that circle into triple crossings. And I'm going to do it by what I call a folding. And the way it works is the following. I take one of my crossing covering circles, so I have this one right here, all right? I'm going to take one of the crossings. I'm going to take the over strand on that crossing, and I'm just going to pull it around the whole circle and then take it out again. So I get a picture that looks like this. Now, to convince you it's still the same knot, imagine this piece going around here is elastic and it wants to pull taut. Notice it's lying on top of everything. If it pulls taut, it'll just pull back to the strand it was before. Okay? So these are actually equivalent knots, but you'll notice 2 things happen. Number 1, I lost a crossing. 1 crossing is gone. And number 2, the remaining crossings on the circle are now triple crossings. Okay? So I've turned all the double crossings on that circle into triple crossings, and I've even lowered the number of crossings by 1 when I did this operation. Okay? So if I have a collection of crossing covering circles, I can do this to every one of the crossing covering circles, and I will now have a projection that has just triple crossings, and I will have eliminated all of the double crossings in the process. Okay, so let's prove that every knot has a triple crossing projection. I'm going to show you 2 different proofs of this. There's actually a 3rd proof due to Von Jones that appears in a paper by Von Jones on the archive from like 2001 that he never published. And when I gave a talk about this and he was in the audience, he came up afterwards and said, actually, I proved that in 2001. I was like, oh, great, thanks a lot. Anyway, so here's the first proof. Every knot can be put in a braid projection. A braid projection meaning that as you move left to right in this portion of it, you never backtrack. You're always moving in the same direction. So this would be a braid projection, an old result due to Alexander. And if I have a braid projection like this, I can easily find a collection of crossing covering circles. Namely, I'll just take the circles that go right around and follow the braid around and pass through all the crossings like this. So there's an obvious collection of crossing covering circles when you put it in the braid form. You fold along them in the way that I just described. Boom, you have a triple crossing projection, okay? So that proves, in fact, that every single knot has a triple crossing projection because every single knot or link can be put in a braid form. In particular, that means we can define the triple crossing number of a knot to be the least number of triple crossings in a triple crossing projection of a knot. So in these two examples right here, the trefoil knot and the figure 8, they have triple crossing number 2 because triple crossing 1, you can't get anything but the trivial knot, okay? But I want to show you a second proof, okay? So this is going to be a second proof that every knot has a triple crossing projection. And the reason I'm going to do that is because the trouble with using the braid proof is when you put it in its braid form, you may have had to increase the number of crossings by a substantial amount. And I'd love to be able to compare the double crossing number, what we normally call the crossing number, with the triple crossing number. So I'd rather not add in a whole lot of unnecessary crossings. So here's my second proof, okay? So we're going to show that every single projection, you give me any projection of any knot, it has a collection of crossing covering circles, okay? And the way we're going to do it is the following. We know that if somebody hands you a projection, you can change the crossings to turn it into the trivial knot, okay? Therefore, there has to be, given any projection, if I ignore the crossings, because I don't care which way the crossings go in order to find a covering crossing collection of the circle, I can get from the trivial projection to it with a finite sequence of Reidemeister moves, because once I turn it into the trivial knot, then I know there'll be a sequence of Reidemeister moves that takes me to the trivial projection. I'll just reverse that process, start from the trivial projection, do my Reidemeister moves till I get to my projection. So what we're going to do is we're just going to show that Reidemeister moves preserve the fact that you have a covering crossing collection of circles, okay? And we'll start from the trivial projection. So does the trivial projection have a crossing covering collection of circles? Yes, it's the empty set because there's no crossings, okay? So now we're just going to look at each of the different kinds of Reidemeister moves. A type 1 Reidemeister move, if I add in a little kink like this, I'll just add one new circle that passes through that crossing. And so now the other crossings we're assuming are already covered by the rest of the covering crossing collection, so now I'm all set, okay? Now I also have to worry about the other direction because it could be that I want to undo a kink and there's a crossing covering circle going through it, but then I'll just pull that crossing out and I'll extend this to the rest of the circle that was already there. So type 1 move, no problem. Type 2 move, now type 2 is a little more complicated. Clearly, if I have a situation like this and I just push the one over the other, I can put in a little crossing covering circle to cover those two crossings. But I do have to worry about the possibility that maybe there was already a crossing covering circle passing through there. But that's not a problem, right? Because as soon as I do my type 2 move, that crossing covering circle takes care of the two new crossings, okay? So it's that's sort of the best of all worlds. I also might want to undo a type 2 move that already has two crossing covering circles covering it this direction. What I do is I do a little bit of surgery on the crossing covering circles to get this little U here of a crossing covering circle, U here. These will extend out to however these extended out, and then I can undo my type 2 move, okay? It's a little more complicated than that. What if I have 3 strands passing through in between and I want to do a type 2 move? First, I do surgery on my crossing covering circles by cutting open these 2 circles and then creating little U's there. Then I do my move. Okay, and I'll still have a valid crossing covering collection. Last case, what if I have an even number of strands passing through? Again, I'll do some surgery on the circles before I do the move, and then I'll do my move and add one new circle. Okay, so type 2 moves are fine. Type 2 moves preserve the fact that we have a crossing covering collection of circles. And finally, type 3, I'm going to do these a little faster, but it's pretty much the same thing. So here, if I have a circle like this and I do my type 2 move, I'm going to take this strand and push it down. Clearly, this circle will do the trick. Here, if I have 3 little strands covering these 3 crossings, I will first do some surgery and change my diagram to look like this, and then I'll do my move, okay? But that'll work. And then finally, the last case is, imagine I have a situation where one circle covers 2 crossings, the other one crosses 1. I do my move. I've still got a part of my crossing covering circle that connects to the old stuff up top, and a part that connects to the bottom stuff, and I've covered everything there. Therefore, I've proved my theorem, okay? So if I have any projection of a knot, I can find a crossing covering collection of circles that cover it, and therefore, I can then fold along those circles, and therefore I can show that there is a triple crossing projection of the knot. The other thing to notice is that means that the regular crossing number is greater than the triple crossing number, because every time I did a folding on a circle, I reduced the number of crossings by 1 when I switched from double crossings to triple crossings. So in particular, I know that the triple crossing number is less than or equal to the crossing number minus 1, okay? Now, let's just think about that statement for a second. So the question is, what knots could actually generate triple crossing number equal to crossing number minus 1? The only ones are ones that have a projection with just one circle in it, because if I had 2 circles, I'd lose 2 crossings, 1 from each circle. So it's only those projections that have 1 circle in them, and I can't serger that one to get more circles, right? So that's the only case, and it turns out this is the only situation that can happen in. This is a 2-braid knot, and the circle goes around like this, and there's no way to serger that circle to get more circles. And when you fold along that, you'll reduce the number of crossings by 1. And so that says triple crossing number is less than or equal to crossing number minus 2 for all knots, except for these knots, which are called the 2 braids. And in fact, we don't even know for sure if these are triple crossing number minus 1. So that's a conjecture, and that's not known. Okay. So we do know that every other knot is going to be triple crossing number less than that. We do not know that these have triple crossing number exactly equal to crossing number minus 1. So it's an interesting open question. Okay, what about a lower bound on triple crossing number? If I have a triple crossing, as I said before, you can expand it into 3 double crossings, and that immediately tells you that the crossing number, the traditional crossing number, is less than or equal to 3 times the triple crossing number. Divide through by 3, and we say triple crossing number has to be greater than or equal to crossing number over 3. Can you realize that bound? Yeah, here's an example. Do there exist knots and links that have triple crossing number equal crossing number over 3? Here's an example of a link where each of these components is actually linked with 4 other components, and so you can show that the crossing number is 24. In this picture, you can see sort of resolved open, split open triple crossings, okay? So these triple crossings, of which there are 8, and because triple crossing number has to be greater than or equal to crossing number over 3, that means the triple crossing number is 8, okay? So here's an example that realizes that lower bound. Can you get a knot that has triple crossing number equal crossing number over 3? And the answer is yes. Here is an example of such a knot. I'm going to tell you a little more about small 2013 in just a little bit. Those are students that I work with during the summer. So this is a knot that has a triple crossing number of 4 and a crossing number of 12. Okay, so there are knots that also realize this lower bound. Okay, so now what I want to do is I want to talk about a relationship with the Kaufman bracket polynomial and these ideas of triple crossing numbers. The Kaufman bracket polynomial was a polynomial that Luke Kaufman discovered in the 1980s, right when there was this flurry of activity about polynomials. It's a polynomial that has a variable a with both positive and negative exponents. And the way you compute it is the following. There's 3 rules. If you take the trivial projection of the trivial knot, its Kaufman bracket polynomial is 1. Okay? If you have a crossing that goes in this direction, so this strand over the other strand, then the Kaufman bracket polynomial, that's what this notation means, the Kaufman bracket polynomial of that particular projection is equal to a times the Kaufman bracket polynomial, where you split the crossing vertically, plus a inverse times the polynomial you get when you split the projection open in the other direction. Okay, so that's what's called a skein relation. So this is a skein relation for that crossing. I have a second skein relation listed here, but in fact it's not really a different skein relation at all. It's this skein relation. If you turn your head 90 degrees, you just turn your head to the side, you would get the exact same thing. But people write it down so that they don't have to turn their head 90 degrees every time they think about this. Third rule just says if you add a trivial component to a projection, you multiply the polynomial by this factor minus a squared minus a to the minus 2. Okay? So you can compute this bracket polynomial for various knots. So if I take the trefoil knot, I can compute the bracket polynomial, and I get this number, a to the 7th minus a cubed minus a to the minus 5th. This is not an invariant for the knot, okay? So it depends on the projection, but you can fix it. And you can fix it by multiplying by a certain power of a, but we're not going to fix it. We're not going to worry about that. We're going to get a simple invariant out of it, and that comes from the span of this polynomial. The span is always just the highest exponent minus the lowest exponent, in this case 7 minus negative 5, which is 12. Okay, so that's going to be the span of the polynomial, and that's the thing we're going to use, and that is an invariant for the knot. Okay, the span will be an invariant for the knot. Okay, very famous result from 1987. One of the things that really proved that these polynomials were useful, proved independently by Luke Hoffman, Kunio Murasugi, and Morwin Thistlethwaite, right about that time. If you have a knot or link, then the span of the bracket polynomial is less than or equal to 4 times the crossing number. Okay, that alone doesn't sound that exciting, but then the second part says, and if you have an alternating knot, the knot is alternating if and only if the span is exactly equal to 4 times the crossing number. Now, what do I mean by an alternating knot? I mean a knot that when you get on it and you travel around, the crossings go under, over, under, over, under, over as you travel around the knot. So this is an example of an alternating knot, and this theorem says, therefore, the span of this knot must be exactly 4 times the crossing number, which is 18, which is 72. Okay? And this is a way of determining whether or not a knot is alternating. You just look and you check whether or not it's true that the span is equal to 4 times the crossing number. And this was used in order to actually show that when you have a knot in a reduced alternating projection, that is the crossing number. You cannot get a projection of the knot with fewer crossings. Okay, so it's a very powerful theorem that they proved and was very useful fact at the time. Okay, so now let's look at triple crossings in the bracket polynomial. So now, because as I mentioned before, there is a BMT crossing and a TMB crossing, we have two different skein relations. They don't look that different, but they are actually somewhat different. Okay, so you have two different skein relations. But it turns out you can prove a similar fact. Namely, if you have a knot or length, then the span of the bracket polynomial will be less than or equal to 8 times the triple crossing number. And the advantage of having results like these, of course, is if somebody gives you a knot and they say, look, I have a projection with this many triple crossings, you can check to see whether or not it's the minimum, right? Because if this is exactly satisfied, you will know that that's the actual triple crossing number and you can't do any better, okay? So this is the extension of the idea that they had in the Kaufman-Murasugi-Thistlethwaite result. Let me just tell you a quick corollary of that. If I have an alternating knot, then it turns out the triple crossing number has to be greater than or equal to crossing number over 2. Now, if you'll remember, the previous result said it's always true that triple crossing number is greater than or equal to crossing number over 3. So this is an improvement on that for alternating knots, and the proof is trivial. Kaufman, Murasugi, and Thistlethwaite said for alternating knots the span is equal to 4 times the crossing number. So writing that out, 4 times the crossing number equals the span. But that result I just mentioned says that's less than or equal to 8 times the triple crossing number, so we get that the triple crossing number has to be greater than or equal to crossing number over 2 for alternating knots, okay? Now, how can you use that? Well, here's a little trick you can do for alternating knots. If you have a bigone in your picture, you can put a little twist in it and turn those 2 crossings into a single triple crossing, okay? So if your entire projection consists of disjoint bigones, you can do this little twisting and you will get a triple crossing number that is exactly crossing number over 2, which is what the lower bound is, and therefore you know that that's the exact triple crossing number. So for instance, if you look at the tables of knots, there's a couple other tricks in here as well, because you'll notice some of my circles actually go around 3, but you can get a similar result. And you can determine the exact triple crossing number for a lot of the knots in the table this way, okay? Okay, but what about higher order? And incidentally, if you're sitting there going, wait, I thought this was going to be a workshop, we'll get to that, I promise, okay? Everybody's going to get to be part of the workshop. Okay, what about higher order crossings? So suppose I have n strands passing through a crossing, okay? So if I have n strands passing through a crossing, in this case I have a quadruple crossing, I'm going to number them with the heights that the strands go through. So 1 is the top strand, 2 is the next strand, 3 is the next strand, 4 is the next strand, okay? So I'm going to keep track of it. TMB doesn't work as well when you get to higher numbers of strands. And I claim I can easily turn a regular projection into a quadruple crossing projection. That turns out to be a lot easier than the triple crossing case, okay? And all I do is I take this understrand that you see right here, and I just swing it back and forth a couple times, and you'll see this is actually a valid quadruple crossing right here. So I've turned every one of my double crossings into a quadruple crossing, and that's a valid way of showing that every projection, every knot has a projection with quadruple crossings, okay? Only quadruple crossings. And so therefore I can define the quadruple crossing number, the least number of quadruple crossings in any quadruple crossing projection. But now there are actually a lot more quadruple crossings. You'll remember we had 1 double crossing, we had 2 triple crossings, we now have 6 quadruple crossings, okay? And that really comes down to the top strand is the top strand, and then as you read clockwise, you just look at permutations of 2, 3, and 4, okay? And there's 6 of them, okay? So there's going to be a lot more of these crossings to look at. So that means there's 6 different skein relations in the case of quadruple crossing. So this is the 1, 2, 3, 4 skein relation. This is the 1, 4, 3, 2 skein relation. Okay, so it gets a little bit messier now. But you can again prove the same result. Or a similar result, span of k is less than or equal to 16 times C4. And then again, for alternating knots, you get this result that C4 is greater than or equal to crossing number over 4. You can use similar techniques to the thing I did for triple crossings, only it gets a little bit messier, to then determine a lot of quadruple crossing numbers. Okay? So we can... Yes, these were by hand. Subsequent ones are from computer, but these were by hand at the time, yes. Okay. So now, I claim that in fact you can turn any knot into an n crossing projection. You pick your integer n. I claim that every knot has an n-crossing projection and therefore an n-crossing number. And here's the argument. It's very easy. If n is even, we're going to do the exact same trick that we did for quadruple crossings. We'll just take every double crossing and we'll go back and forth the right number of times, and you can get away with that, and that'll always work to give you an n-crossing projection if n is even. If n is odd, we'll just use what we already know. First, we'll turn it into a triple crossing projection, and then we'll use this trick of going back and forth, and we can get 5, 7, 9, etc. And so then we can turn it into an n-crossing projection for any n odd. Therefore, we now have an n-crossing number for every integer n greater than or equal to 2. So now we have a spectrum of numbers instead of a single number, which is what the crossing number used to be. There's now a spectrum of numbers. So in the case of the trefoil knot, its double crossing number is 3, its triple crossing number is 2, and its quadruple crossing number is 1. Okay, which I'm going to come back to because that's kind of an interesting fact. The quadruple crossing number is 1 for the trefoil. Okay, real quick, going back to the span, this is the result that Kaufman, Murasugi, and Thistlethwaite proved. This is the result for triple crossing, quadruple crossing. Any guesses as to what this is going to be? Any thoughts? Any other guesses? 24. Sorry, I set you up for that. It turns out it's 24. It's not 32, which is certainly what I thought it was going to be for a long time. Quintuple crossing projections are starting to get messy. Here is a skein relation for a quintuple crossing projection. There are 24 different quintuple crossings. Okay, this is one of them. We have 24 of these kinds of pictures. And so things are getting a little bit messier, which makes it harder to actually figure this stuff out. In fact, we'll call the width of a skein relation is the highest power of a that occurs minus the lowest power. So in this previous slide, you'll notice there was an a squared at the top and an a to the minus 10th. So the width of this particular skein relation is 12. Okay? So the width of that one, of that particular crossing, skein relation is 12. Okay, so let's just take a look at the realized width for n crossings. So when n equals 2, so if I look at 2 crossings, as I said, there's only one type of 2 crossing, and the width of the skein relation is 2. For n equals 3, there are 2 different kinds of crossings, and the width of the skein relation is 4. For n equals 4, 6 types of crossings, the width of the skein relation is always 8. Here where things start getting messier. When n equals 5, there's 24 different crossings, so 24 different skein relations, and they start having different widths, okay? So different skein relations for, different widths for skein relations. When n equals 6, there's 120 crossings, different crossings, and they can have these widths. N equals 7, 720 crossings with these widths. N equals 8, this is as far as we went. 5,040 different 8 crossings, okay? Those are all the possible ways you could create 8 crossings, and they have all these different widths. So that makes things get messier as you go up. But in particular, small 2013, I'll introduce you to them on the next slide, is a group of students I was working with. And so what we proved was this fact, that the span of the bracket polynomial is less than or equal to the greatest integer less than or equal to n squared over 2 plus 4n minus 8 times the n crossing number. So we get this lower bound on n crossing number, which then allows you to actually determine n crossing numbers for various n. So this is the small group. Small is a program we run at Williams College with funding from the National Science Foundation Research Experiences for Undergraduate program. It's been around for 30 years now. We get amazing applicants. We get some of the best undergraduates in the country. Typically, we get 400 applicants for 40 positions at most. I usually work with a group of 6 or 7. This is where all these students who were undergraduates at the time this was taken are in graduate school now. Very, very strong group. I'm going to mention Daniel Vitek again in just a little bit, who's the guy right there on the left. But very, very strong group. So they were great. So here is a table. I know you can't see it very well, but here's a table of multi-crossing numbers. So up on the left, in the upper left corner, these are the knots. 3, 1, the trefoil knot, 4, 1, 5, 1, 5, 2 going down. These are some composite knots, and so the knots are just coming down here. These are the numbers that we've known for a long time, the double crossing numbers. These are the triple crossing numbers, quadruple crossing numbers, quintuple crossing numbers going down. And I know you can't see this very well, but I want you to note the holes. So for instance, I don't even know what the triple crossing number of the 7-1 knot is, which happens to be one of those 2 braids that I mentioned before, that open question. We still don't know what the triple crossing number of that knot is. And so there's some holes even pretty early in the catalog of these numbers. And then as you go up, you'll notice the holes get more and more, okay? Let's take a look at a close-up of the beginning of the table. So this is the trefoil, figure 8, etc. And you'll notice they go 3, 2, 1, 1, 1, 4, 2, 1, 1, 1. One thing to notice is all 3 of these knots, 6, 2, 6, 3, and 3, 1, sharp 3, 1, which is a composition of 2 trefoils, have exactly the same spectrum. So if you were hoping that spectra would tell apart all knots, sorry, it's not going to happen, okay? Can always hope, but no. Okay? What other ideas from knot theory generalize to these end-crossing projections? So here's one, braids. So as I mentioned before, Alexander's theorem says every knot or link can be put into a braid form. And so here's a two-crossing braid, a braid with all two crossings. Well, you can also make three-crossing braids, a braid with all three crossings, okay? And that student I mentioned before, Daniel Vitek, he asked the following question. Given any fixed number n greater than 2, does every knot or link have an n-crossing braid projection? So does it have a projection like this one on the left for 3, a 3-crossing braid projection, okay? And so he asked that of one of my students. This is Daishiro Nishida, who just did an undergraduate thesis with me over the last year. And so he asked this question. And the answer in the case of n equals 3 is no. And Daniel knew that, okay? Namely, if n is odd, you can't realize any knot. And the reason is very simple. If you think about a braid presentation of a knot with triple crossings in it, and you label the strands at the top odd, even, as you go across 1, 2, 3, odd, even, you'll notice any triple crossing preserves the odd strands and the even strands, which means by the time you're done, when you cycle around and close the braid, you're going to get at least 2 components. You'll get one corresponding to the odds and one corresponding to the evens. So you can't get a knot. You can get a link potentially, but you can't get a knot. So you're never going to get every knot. For any odd n, you're never going to get a braid presentation for that. But what Daishiro did prove was the following. For every even n, every single knot and link has an n-crossing braid projection, okay? And, braid theory has turned out to be a really interesting area that has incredible applications to algebra as well as topology, and so this is sort of an interesting take on that. So for every even n, every knot or link has an n-crossing braid projection. Moreover, if you do go to the odd n, so long as you have at least 2 components, you're not a knot anymore, but you're a link, you also can realize that in an n-crossing braid projection. So what that says is, every knot and link has a spectrum of braid numbers now. So you can do the 2-crossing braid number, the 3-crossing braid number, the 4-crossing braid number, and you can find higher order braid indices. So you can find these higher order braid indices for any knot or link, and that's an open question, is to find any of those. Okay, so these are pictures of multi-crossing braids. Okay, so here's a question that comes up from what I was saying before, and that is, does every knot have a projection with a single n crossing for some n? We said before that the trefoil knot does have this property, okay? So this is actually a picture of the trefoil knot if you put the crossings in the right way. We're going to call a projection like that an Uber crossing projection. This was students' choice as to what we were going to call it. So this is an Uber crossing projection. So it's a projection with a single n crossing. And you'd like to know, does every knot have such a projection? Here's a really nice one called a pedal projection. So you remember the last one, I had some nested loops. What if none of my loops are nested? This is what I would call a pedal projection. And an obvious question is, do knots have pedal projections? Can they be realized in pretty pictures like this? And you'll notice here, I have some numbers on here. I don't know how well you can see them, but this means this is the top strand 1, and then it goes to 3, and then it goes, et cetera. And I can go down and I label each of the strands what level they're going through, and that completely determines the knot that would result, okay? So this is what we call a pedal projection. And this is the group where we looked at pedal projections. So this is small 2012. This is where they're in graduate school, except for Si-Jung Park, who was a postdoc at the time. But this is where these students are in graduate school. Tom Crawford's the only one that's not in that picture. And we proved that, in fact, every knot does have a pedal projection. Okay, so every knot has a pedal projection. And that means, in particular, you can define the so-called pedal number of a knot to be the least number of loops in a pedal projection of a knot. Okay? And so let's look at an example here. And I have this example right here. You can make these 3D printers. So this is a 3D printed version from the side view. It doesn't look very special. But from the end view, you realize that it actually is a pedal projection. So I'm going to demonstrate this with this other model that I have here. Okay? So from the side view, looks ugly. Can you see that shadow there? Looks ugly, but then you turn it just right. Whoops. And you can see the pedal there. You can see the pedal diagram. Yeah, so kind of interesting. And so what that says is you can describe every knot simply as a permutation on the n numbers 1 through n corresponding to the levels these go through. So 1 goes to 3, goes to 4, etc. And so this is a very, very simple way of describing knots, this idea of pedals. It doesn't work nearly as well for links, and if you're interested in that, you should talk to Jason Parsley, who's thought a lot about what links look like when you start dealing with pedal diagrams. Okay, here comes the workshop portion, okay? So I said it was a workshop, okay? So everybody, this first part's sort of silly. Take your left hand and cross your index finger with your middle finger, okay? Take your right hand and just without a crossing, put your two fingers there, from there to there, okay? Pedal projection of the trivial knot. There you go, okay? All right, so that was the silly part, okay? Now I need 5 volunteers. I need 5 volunteers who are willing to come down here, okay? Who is willing? Yes, there's going to be some hand-holding going on. 5 volunteers. Rob, of course, will come down. Yeah. Great, good. 1, 2, 3, 4, 5. Okay. Yeah, long arms help. Okay, here's what we're going to do, okay? We are going to make a pedal knot. And so what I want you to do is the 5 of you, I want you to stand in a pretty tight circle, shoulder to shoulder, okay? And what we're going to do is we're going to make this particular pedal knot right here, okay? And so what you're going to do is you're going to first cross your hands, okay, in front of you. And it doesn't matter which way you do it. We'll fix them later, okay? And then ignore the 2 people that are just to other side of you and look at the 2 people who are farther away from you. So ignore the people at your shoulders and look at the other people. And you are going to take with your left hand, you're going to take the right hand of the right person. Yes, and with your right hand, you're going to take the left hand of the left person. Okay, you guys look pretty good, I would say. I think that looks pretty good. Okay, now what we're going to do is we're going to fix the crossings, okay? Because right now this is going up and down. It's going to be interesting, so we'll see how well this works. Okay, we are going to make you 1, 3. So that means you're going to be 1. I'm going to switch hands here, sorry. Like that. That's the 1. And then the 3 is going to be the next hand. So let's move this one up a bit. Yeah, and we're going to put it there for now, though we may move the other one later. Okay, so that goes 1 goes to, so 1 goes to 3. Now 3 goes to 5. So we're going to take your other hand here and go all the way to the bottom. 3 goes to 5. And then Jason, you are, I did 3 goes to 5. 5 goes to 2. So you're going to go to 2. Good. And then, all right, so 5 goes to 2. And then 2 goes to 4. So you guys go to 4, and I think we're good.
Now we have to make a nice and top.
Now what have you done?
So we have created now. We're going to do 2 things. Okay. Do you think if we move you guys around, will you be able to recreate this?
Well, we can all just dance, right?
Okay. Well, this is what we're going to do. So first, what I want you to do is try to disentangle. You're not going to be able to disentangle because this is the trefoil knot. We'd like to see it's a trefoil knot, but I'd like you to try to disentangle enough so the audience can see that it is the trefoil knot. So yeah, I pull out that top. Yeah, it's good. I've never tried to do this before, by the way. Oh, that was good. I think you did it. Oh, no, let's see. Rob, you have to turn around. Go under your own arm. Okay. And
We have 3 crossings, right?
well, Jason's got an extra one there. Jason has to turn around, too. Good. Okay, good. And that's a trefoil knot. Good. Nice job. Okay, now, can you go back to the knot?
To the pedal?
Yeah, yeah. Just out of curiosity. No.
But Rob was on my right.
Yeah. No. Because I was in Jason.
Rob was opposite.
Uda was over here before. I remember she was over here.
Klaus, you're in between now. I was opposite.
You were on my other side.
Move back.
But okay, so what's the difference? You were on my right side, yeah, for sure.
And you need to have your hands crossed somehow. There. Oh, that's right. There you go. Oh, I'm impressed. That was very good. Okay, good. Okay. So now what I'm going to do is I'm just going to make one little change.
1 and 3 anymore, but that's like.
You're gonna unknot us?
Yeah, I'm going to unknot you. So what we're going to do is we're going to just take the top strand and we're going to go under. In theory, you should be the trivial knot. Good luck.
Woodson noticed that you were no longer in the same pedal.
Okay, that's okay. Yeah. Oh, you guys are doing good. You're close. Oh, here's an interesting. This will be interesting.
Backflip.
You need to bring the arm. He needs to step over this pair of arms. Yeah. Here, I'll hold you so you don't tip over.
I have the very best medical insurance.
Okay, and then keep going, keep going, keep going. Keep going, around, 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 around. There they did it, okay, big hand, thank you. Good job, everybody, nice job, thank you very much, that was great. Okay, so I'm gonna explain to you real quick, how do we know that every knot has a pedal projection, okay? And it really is by an algorithm. So we have an algorithm, somebody gives you a projection of a knot, you can turn it into a pedal diagram. And here's the way the algorithm goes. I'm not gonna spend a lot of time on it, but it's actually very straightforward. You start with your projection, you move things around in the plane so that all the crossings are on a single vertical line in the plane. So I'm just gonna push things around so I can get them all on one line, okay? And you can always do that. You can always make sure that you can just push your crossings around to get them all on one line. I'm gonna take the farthest right point, put an orientation on my knife, and travel around, and each time I get to a crossing, the first time I hit it, I put an O on if it's an overcrossing, and a U on it if it's an undercrossing. So I start here, and I say, oh, that's an overcrossing, I put an O there. Come here, that's an undercrossing, I put a U there. Go here, that's an overcrossing, I put an O there, and then that's it, I'm done because I've already hit all the crossings, okay? So I'm gonna label every crossing with an O or a U. Now, I'm gonna take all the O crossings and push them a little to the right of the line, and I'm gonna take all the U crossings and push them a little bit to the left of the line. So I'm just gonna push things over a little bit, okay? Planar isotopy, okay? Now I'm going to rectilinearize everything so that everything is on a vertical line or a horizontal line. You can always do that. And I could have a lot of, lines here, but I don't want to make it too complicated. And in fact, if I can get rid of some vertical lines, I will. And so I can actually do this to get a picture that looks like this, okay? And I can always do this, okay? But keep in mind, these are, the first time I hit them, these are the overcrossings. First time I hit them, these are the undercrossings, okay? Now I'm just going to manipulate this picture. Right now I want you to think of this picture as being in the YZ plane with the x-axis coming out towards us, okay? Here's what I'm going to do. I'm going to get on my knot at my initial point. I'm going to travel along this line, which is in the YZ plane. Then I'm going to go down, and the next horizontal line that I hit, I'm going to turn it counterclockwise out of the YZ plane a little bit, okay? And when I do that, that's going to also take this vertical line and tilt it a little bit. But I'm going to just turn this a little bit out of the YZ plane. Then I'm going to go to the next horizontal line. If I go straight up, I hit my next horizontal line. And I'm going to rotate that even a little farther out of the YZ plane. Okay? And I'm just going to keep doing this as I travel around my knot. Each time I come to a horizontal line segment, I'm going to turn it even a little bit farther out of the YZ plane in the counterclockwise direction. Now I'm going to look down on this picture from above. And when I look down on this picture from above, it ends up looking like this. Because I went and I turned the first line, then I have a vertical line that just looks a little bit slanted, so it looks like that. Then I turn the next one a little more, the next one a little bit more, and my picture ends up looking like this. The other thing to notice is the way I'm turning it respects the overcrossings and the undercrossings. I don't have to worry about getting the wrong thing because I put the overcrossings on the right and the undercrossings on the left, and that respects it. Okay, so I get a picture that looks like this, which if I clean it up looks like this. And this is in fact an uber-crossing projection of the trefoil knot, okay? So I've actually succeeded in getting an uber-crossing projection. And this will always happen like this, and it'll always look very similar to this, namely it'll always look like I've got n over 2 loops here and n over 2 minus 1 loops here and 1 loop on the outside. Last step, this is what we call a pre-pedal diagram, is take that outer loop and just pull it down and turn it into 2 more pedals. And so not only did we get an uber-crossing projection, but we actually got a pedal projection out of it. Okay, so here's an algorithm for turning any knot projection into, in fact, a pedal diagram. And so then we can actually list pedal numbers for knots. Notice the knots always have pedal numbers that are odd. So the trefoil knot had 5, as we saw already. 7 pedals, 9 pedals, and then these are actual permutations that generate them, although there certainly are many permutations that will generate a given knot. Okay, so we can figure out these pedal numbers for knots. What can you do with it? Well, Joel Haas and his colleagues all from Israel have written a couple of papers where they use pedal projections to generate random knots. So this whole field of random knot theory where you want to generate random knots and ask questions like, what will be true of various invariants that we associate to knots when you look at them randomly? What's the distribution of those invariants? What can you say? It turns out that this pedal model is very convenient because it's really easy to generate a random knot. All you do is generate a random permutation on n elements. And as you generate those random permutations, you're generating random knots. It has certain advantages over other systems in that a lot of the other systems for generating random knots generate little compositions of little trefoils a lot. And those make it hard to calculate invariants like hyperbolic volumes, things like that. They aren't hyperbolic. This avoids that, as it turns out. So they've written a couple of papers about this called the Petaluma model because they were talking about pedal knots and they just so happened to be in Petaluma at the time. So that's why it's called that. So I said that already. Okay, now, I want to talk a little bit about hyperbolic volume, which is an area that I'm really interested in and how it relates to these multi-crossings, because there's some really beautiful combinatorics that's associated with this. This is a fact due to Thurston. Thurston proved back in the 1970s that knots fall into three categories. You can have a torus knot that just sits on the surface of a torus without any crossings. You can have a satellite knot, where you take a knot, like this one right here, you thicken it up, and you put another knot inside it as if it's orbiting the original knot. That's why it's called a satellite knot. It stays within a certain neighborhood of the original knot. That's a satellite knot. And what Thurston proved, which is a really remarkable theorem, is that if you look at all knots, every knot is either going to be a torus knot, or it's going to be a satellite knot, or it's going to be a so-called hyperbolic knot. Okay, and I'll tell you about hyperbolic in just a second, but this is really one of the most amazing theorems. It's actually broader than this. It's for three manifolds, but in particular, this is what it says about knots. And it's just an incredible fact that really revolutionized low-dimensional topology in general and knot theory in particular, this fact. So what do I mean by a hyperbolic knot? A knot is hyperbolic if space minus that knot, the complement, can be given a hyperbolic metric, a metric of constant curvature minus 1, okay? So that's what it means to be hyperbolic. Now that alone doesn't sound that interesting, but there is this theorem called the Mostow-Prasad rigidity theorem, which implies that if you have a hyperbolic knot or link, you can actually calculate its volume. So the volume of space minus that knot, you'd think it would be infinity, but it's not, and it has a unique volume associated with it. So there's a unique volume associated with every hyperbolic knot. So for instance, here's the table of knots. That's a torus knot. The trefoil knot is a torus knot, so it has 0 for its hyperbolic volume. There's another torus knot right there. There's another torus knot right there. But for the other knots, like the figure 8 knot, it has a volume of 2.02988, ... That number right there, for instance, nobody knows if it's rational or irrational, algebraic or transcendental, and the number theorist would love to know the answer to that question. So there's a lot of really interesting stuff going on with these hyperbolic volumes. And then as you notice, as the knots go up, the hyperbolic volumes start going up. And this is a way of distinguishing between knots. There are computer programs now that you draw a knot, and it will compute the hyperbolic volume for you. You draw a different knot, and it'll compute the hyperbolic volume. And if they're different, then the knots have to be different. Okay, so it's a really good way of distinguishing knots. It was used heavily when people actually tabulated all of the prime knots through 16 crossings. They used this idea, and it was a very powerful fact. Okay, so I mentioned Bill Thurston proved that big theorem. This is actually a result of Dylan Thurston, who happens to be the son of Bill Thurston. And Dylan Thurston showed that if you have a knot and you want to decompose the complement, you can decompose the complement into octahedra, one for each crossing. So here you see a crossing here, and you see this octahedron that I've drawn right here. And what you do is you take this vertex and pull them up to a finite vertex above. You take the front vertex and the back vertex and you pull it down to a finite vertex below. And if you do this at every one of the crossings and glue together the faces appropriately, you can fill up the entire complement of the knot. It's really a beautiful combinatorial argument that he proved. Now, it turns out that if you have hyperbolic octahedra, you can show that the volume of a hyperbolic octahedron has to be no more than 3.6638, okay? And yeah, sorry, in this particular octahedron, there's an ideal point here where the knot is missing and an ideal point here where the knot is missing, but the other 4 vertices are actually all finite vertices. But, and I'm glad you mentioned that, when you get an octahedron that has volume 3.6638, it actually has to have all of its vertices ideal. So this particular octahedron will actually be less than 3.6638 in its volume, okay? But conclusion, if you have a hyperbolic knot, its volume is less than or equal to the crossing number times 3.6638, because I have this octahedron at each crossing, so I have an upper bound like that. All right, so now let's look at multi-crossings. What about for a triple crossing? I take my original octahedron and I skewer it with the middle strand, okay? Then I cut it open along these faces, and I actually get 2 octahedra. So one between the top strand and the middle one from the middle to the bottom, okay? So we can decompose the complement, and then you can do this at every triple crossing, and you can decompose the complement of the knot into octahedra, 2 for each triple crossing, which says, therefore, the volume is less than or equal to 2 times the triple crossing times 3.6638, okay? And, you know, so it seems pretty clear what's going to happen. And this is joint work with Greg Keeney, who did an undergraduate thesis with me, now a graduate student at Carnegie Mellon. And so quadruple crossings, we just figured the same thing was going to happen, but things got interesting for quadruple crossings, okay? Remember, there are 6 different quadruple crossings. Up to reflection, there are 3 different up to reflection, okay? The first one is a 1, 2, 3, 4, and yes, it has an octahedron at the top, octahedron in the middle, octahedron at the bottom. This is a particular crossing 1, 2, 4, 3, octahedron, octahedron, octahedron. This is the interesting one, okay? 1, 3, 2, 4. It has an octahedron at the top. It has this thing that is what I'm going to call an 8 bipyramid. It's 2 pyramids stuck together on their base, 8 edges all the way around the outside, and then another octahedron on the bottom, okay? So that's what I'm going to call an 8 bipyramid. We'll talk about bipyramids in just a second. Here is a quintuple crossing. Kind of ignore the outside stuff, which was for the argument we were making. This is a quintuple crossing with a octahedron at the top. Notice an octahedron is a 4 bipyramid, then an 8 bipyramid, then an 8 bipyramid, then a 4 bipyramid, okay? So you'd love to understand, what are the possibilities for these octahedra and bipyramids for the various kinds of crossings. And so this is a bipyramid, so this would be a pentagonal bipyramid, a 5 bipyramid. When you actually put these in hyperbolic spaces, ideal n bipyramids, this is a picture using the upper half space model of hyperbolic space, it might look something like this. And these things have very interesting properties. If you look at the volumes of n bipyramids, so right here was the octahedron, and I said the biggest volume it can be is 3.6638. The interesting thing is as you increase the number of edges defining my bipyramid, the volumes go up very slowly, actually logarithmically. So if you take a billion bipyramid, its volume is only 125. Okay, so it turns out to be a very cheap way to get volume. If I had taken that billion bipyramid and cut it up into a billion tetrahedra, which I could easily do, we happen to know that the volume of a tetrahedron is no more than 1.014, but then your bound would be like a billion. So putting it in bipyramid form actually saves a huge amount of volume. Okay, so here's the result that Greg and I proved. So suppose I have an n crossing, call it C. So this is a crossing, and I've got some permutation that I've chosen. And I'm going to let capital M of C, the crossing, comma I, be the size of the bipyramid between the ith level and the I plus first level. Okay, so I just want to look at the sizes of the bipyramids. Here are the rules. Rule number 1, top bipyramid has to be an octahedron. Bottom bipyramid has to be an octahedron. So it'll always be true that the top one and the bottom one have to be octahedra. Rule number 2, if you have some size of your bipyramid at one level, the next level has to differ from it by 4 or 0. Okay, so it can either go up by 4, down by 4, or not change at all. Okay, so that's the rule for one bipyramid and then the next bipyramid in the level. And then number 3, that's it. Every possible sequence of positive integers that satisfy 1 and 2 is realized by some permutation for a particular crossing. Okay, so let's, as an example here, suppose I have a 12 crossing. So these are the strands of the 12 crossing, 1, 2, 3, 4, 5, 6. Here I'm going to show you the size of the bipyramid that I want at each level. And so I can have a 4 bipyramid, 8 bipyramid, 12 bipyramid. For this particular example, I'm going to start with a 4 bipyramid at the top as I have to. Then I'll go up to 8, 12, 12, 12, 8, 12, 8, 12, 8, 4. Okay, so I want to realize that particular choice of bipyramids that satisfy those conditions that we saw on the previous slide. And so there's actually an algorithm which then allows you to create the permutation that would correspond to that. In this particular case, it would be 1, 4, 5, 12, et cetera. And you follow this pattern, you can actually generate the crossing that would generate that particular set of bipyramids that you want in that particular case. Okay, so we can use this to bound volumes in terms of the permutations that make up the various n crossings. Okay, so now I think I am going to skip ahead to, I'm going to skip some stuff here because we're going to go to questions at the end. I'd rather talk about the questions. So there's some pretty pictures that you won't see. Okay, so questions. How can we recognize an unknot from its petal diagram? Okay, so somebody gives you a petal permutation and they say, is this the unknot? So here's an example here. There's no obvious way to simplify this and say, oh yeah, that's got to be the unknot, the trivial knot, because you can do these moves. And so it'd be really nice to have sort of a set of moves that allows you to get from any one petal permutation for a knot to any other petal permutation. Number 2, are there certain categories of knots for which this idea of petal knots makes a lot of sense? It turns out that a lot of the sort of extreme cases with petal knots come out of the n+1 torus knots. They are sort of particular examples that really seem to like petal diagrams in particular. As we've said, for any knot, There always is an n crossing number that's equal to 1. Eventually it goes down to 1. But what you'd like to know is it true that the crossing numbers are always non-increasing? Do they always go down C3 greater than or equal to C4 greater than or equal to C5? We don't know that. We do know the following two facts. We know that the even ones are non-increasing, and we know that the odd ones are non-increasing. But it is, it is conceivable that you could have a multi-crossing number for some number that's 7, and then the next one could be 8. We do not have a proof that they can't go back up again, and so that's still open. So that's kind of an interesting question. I told you how the span of the bracket polynomial is related to multi-crossing number. What about the uber crossing number and the pedal number? How is span of bracket polynomial related to that? Moreover, you'd love to look at the knot homologies, Kovanov homology, grid homology, and figure out how those are related to uber crossing number, pedal crossing number, and n crossing number. So that would be very interesting to look at. And more generally, this is kind of the general question. Take your favorite idea that applies to double crossing projections and generalize it to higher n crossing numbers. So you decide what your favorite thing is. It could be unknotting number, braid index, stick number, bridge number, hyperbolic volume, supercrossing number, Reidemeister moves, virtual knots, quandles, etc. And just ask the question, well, how does that actually relate to n crossing numbers and pedal numbers and uber crossing numbers? Okay, and I will stop there. Thank you very much for listening. Thank you. Do it.
How does crossing numbers behave in connected sum?
That is a very good question, actually. So there are some weird things that happen. You can actually take two knots with, I'm trying to remember when it first happens. I think it maybe happens with quadruple crossing number. You can take two knots where when you take connected sum, you can actually drop the, instead of just getting the sum of the two quadruple crossing numbers, you can get something less than that. So they don't always behave well, as it turns out. It's still open how they behave for triple crossing number. I don't actually know the answer to that, but certainly for higher crossing numbers, they definitely do not behave the way that we expect double crossing numbers to behave. Yeah. Yeah. Yeah, so the question was, are there different hyperbolic knots that have the same hyperbolic volume? And the answer is yes. The first time it happens is the 5-2 knot, which is a 5 crossing knot, and a 12 crossing knot. That's the first time it happens. So it's rare for low crossing number. It also is true if you've heard of what's called mutation. So mutation means you've got a tangle with 4 strands coming out, and then the rest of the knot over here, and you cut along those 4 strands, flip, and then glue back in, and you can flip this way, you can flip this way, or you can rotate 180 degrees. Those are all mutations, and the volume is always the same for those. So mutants of each other always have the same volume. So there are cases like that. Yeah, Dorothy.
So eventually, as you get down to the supercrossing, do you have any conjectures? Maybe I'm just naturally loud.
She's recording it, actually, so she would love for you to speak in the microphone, yeah.
Beautiful talk, Colin. Really gorgeous.
Thank
I
you,
wish we
Dorothy.
had seen all the other slides. Okay. So I'm wondering about as you go down to the, or possibly with little blips, go down to the Uber crossing, do you have any conjectures about the length of that sequence for families of knots or relationship? Yeah.
Yeah, no, that's a great question. I mean, I think there's a ton of open questions related to that. I do think there are going to be certain categories of knots where you kind of go down fast and that's it. And there's going to be other ones where it could take a while to get there. And that's sort of the big open question is, how do you eyeball it and determine which one it's going to be? And I have no idea on those kind of questions at this point. I think there's tons of interesting questions to ask. I think that's a good one. Yeah. Yeah, Rob.
Two questions. One, we were up.
Also a great talk. And that dance was a lot of fun. So we were up there, and you knew what permutation, how to shift the permutation to get us to the unknot.
True.
Now, I think you said, so this is the first question, I think you said that recognizing the unknot is difficult. Is there
Yes.
any characterization of the permutation that tells you something? I mean, maybe it tells you.
So the way I knew what to do for that particular one is that the first time you get a non-trivial knot is when you have a particular permutation for 5, right? So
Yeah.
I made you the trefoil knot to begin with.
And
And the
change it.
rule has to be, if you're going to make a non-trivial knot with that few number of petals, is you cannot have a person who has two levels next to each other. So you can't have a 2-3. Because if you have a 2-3, that person could step through the crossing and you would lower the number of pedals. And so I knew that I had the right permutation to start, and if I switched any two of those, I would actually get a person who would have two adjacent heights, and therefore it'd have to be the trivial knot.
So the other question had to do with hyperbolic volume, and I'm trying to remember what the inequalities are, so I may mess this up, but you know a lot about the hyperbolic volumes, and you have inequalities going one way, but are they sort of two-sided inequalities? You know what I mean? Are they? Yeah, let me leave it at that.
Yeah,
You
no,
interpret.
I mean, there are, yeah, so all the inequalities I showed you were upper bounds on volume, okay? And the techniques that I'm talking about here, it's all about upper bounds on volume. Lower bounds on volume, there are some, but they're harder. They're a lot harder to come by. There's this work of Ian Eagle's, Thurston, Storm, where they talk about the guts of a manifold, and that is one of the few ways to get lower bounds on volume. In general, it's much harder to get lower bounds than upper bounds. But there are certain cases where you can get lower bounds using techniques like that. So in terms of these multi-crossing numbers, in general, I do not know lower bounds in terms of multi-crossing number. I'm trying to think if there's any lower bounds that anybody knows for that, but I can't think of any off the top of my head. So my guess is that's open, and you could use techniques like Ian Eagle and company used in terms of guts of manifolds to do that, but nobody's done it. Yeah, it's a good question.